Hello everyone, and welcome to our second session of the Geology of Scotland course. In the previous session, we had an introduction to the course, we discussed a few key notions, and we gave a brief summary of the sessions to follow. Scotland is more than 3,000 million years old, and it's made of 5 terranes, or fragments of continental crust, that for most of their existence evolved independently of one another and gradually merged together. Of the remaining 5 sessions, each is dedicated to one of these terranes. We will discuss the geology associated with them, and we will review the formation and deposition of major rock groups. This session is dedicated to the Hebridean Terrain, the oldest of the crustal blocks that make Scotland. The Hebridean Terrain is part of the North Atlantic Craton, an ancient piece of lithosphere that contains one of the oldest fragments of continental crust and the underlying upper mantle. The North Atlantic Craton began to form about 3,800 million years ago. It eventually stabilized, then began to come apart with the breakup of the supercontinent Pangaea about 150 million years ago. Its remnants are now scattered across North America and Europe, as it was further dismembered with the opening of the North Atlantic Ocean. The Hebridean Terrain is a terrain of geological contrasts, as it features both the oldest and the youngest rocks in Scotland. The Isle of Skye in particular is almost like a Scotland in miniature. If we take a closer look at it, we see that on its relatively small area, it has rocks representative of all major divisions of geologic time. The oldest rocks in the Hebridean Terrain, which are also the oldest in Europe, are represented by the Lyrician Complex. As we can see on this map, the rocks of the Lyrician Complex outcrop in all of the outer Hebrides, some of the northern inner Hebrides, plus the islands of Cole and Tiree, and a narrow belt of mainland between Cape Wrath in the north and Loch Thoridone in the south. An important mention here is that what we see on this map is only the outcrop area of the Lyrician Complex. That is, where these rocks are exposed to the surface of the Earth. The overall extent of the Lyrician Complex is assumed to be much larger. For example, the rocks extend beyond sea level on significant areas of the continental shelf, both to the north and west of the outer Hebrides, and also across the Minch and the Sea of the Hebrides. Also, many of the blank areas on the map, where more recent rocks exist, are also underlain by rocks of the Lyrician Complex. This is arguably one of the biggest limitations of mapping, at least of two-dimensional mapping, that we can only get to see what is at the surface and not the actual area covered by the rocks. If you remember from the previous session, complex refers to rocks that have different textures and are often also genetically different. Therefore, the Lyrician Complex is a very general name for rocks that formed in different locations at different times and in different tectonic settings. The one thing they have in common is that they are of Precambrian age, which is also a very general term for the first 4,000 million years of geologic history. So let's have a look at what exactly this complex is made of. By far, most of the rocks that make up the complex are gneisses. These are metamorphic rocks that form in conditions of high temperature and pressure, usually as a result of previous rocks having suffered intense and sometimes multiple cycles of bearing, heating, and partial melting. They have a foliated texture and an easily recognizable appearance, with alternating bands of darker and lighter colors. These gneisses are the reason why the Lyrician Complex is also often referred to as the Lyrician Gneiss Complex. The original rocks that underwent physical and chemical transformation to eventually become gneisses are called parent rocks. A more specialized but less friendly term is Protolithe. Most of the parent rocks of the Lyrician gneisses were plutonic rocks. And again, if you remember from our last meeting, plutons are accumulations of magma that cools down and solidifies into a variety of bodies before reaching the surface. The plutonic parent rocks of the Lyrician gneisses were in fact an association of plutonic rocks, collectively known as the TTG suite, which is an abbreviation for tonalite, tronjamite, granodiorite. You'd probably think that this is one of those terms that has the gift of making geology instantly unlikable, but it's not the case really, and I wouldn't mention this association of rocks if it wasn't interesting or at least intriguing. These terms define both types of magma and the rocks resulting from the consolidation of the respective magmas. Rocks of the TTG suite have a very similar composition with granites, so we may as well refer to them as granitoids. But then we would miss the interesting part. This association of rocks formed everywhere around the world in the time interval between 4,000 to 2,500 million years ago. That is the entire span of the Archean Eon. In the case of the Lyrician Complex, they formed between 3,000 to 2,700 million years ago in subduction areas by partial melting of oceanic crust. This happened under very specific conditions that were unique to that time. In the Archean, conditions were very different from now. The temperature in the upper mantle was about 3-4 times higher. Not only plate tectonics was very well developed, but the plate movement was faster. There were more subduction areas, and oceanic and continental crust were created at a higher rate than they are now. While the exact formation mechanism of the TTG suite is still debated, it is believed that, compared to present-day conditions, back in the Archean, because of the higher temperature of the upper mantle, when a portion of the oceanic crust was subducting underneath the continental crust, it would melt almost immediately. Therefore, subduction likely occurred at a very low angle, and the mantle wedge was either very reduced or missing. The mantle wedge is this roughly triangular area, the portion of upper mantle located between the subducting and overriding plate. Because of no mantle wedge to cross on their way up, the TTG magmas would be made of relatively light elements. Later conditions changed. The upper mantle temperature began to rise, and subduction occurred at a higher angle. Then the magmas would travel the mantle and would be enriched with heavy minerals specific of it. However, the more time passed, the rarer the TTG magmas became, to the point that nowadays they don't form anymore. The TTG suite is considered the signature of the Archean, and indeed, in ancient cratons that preserve continental crust of that age, the TTG suite are the dominant rocks. Now that we've seen who the parent rocks of the Lyrician gneisses are, let's see how they transformed into the famous gneisses we see today. As small terranes collided with each other, the plutonic rocks were caught into a series of orogenic episodes or mountain building events. The first was a high-grade metamorphic episode, the Badkalian, which caused the parent rocks to be buried and exposed at very high temperatures and pressures. This is essentially how the Lyrician gneisses formed. But the Badkalian was not the only one. It was followed by another episode, the Inverian, a medium-grade metamorphic episode that was about half as intense. Because of the immense time span involved, it is very hard to create a precise chronology of the events. But it is usually believed that the Badkalian occurred 2,700 million years ago, while the Inverian 2,500 million years ago. Now, these two orogenic events were followed by intrusions of magma into the recently formed gneisses. This is the famous Scory Dike Swarm, which is a major reference point in the overall chronology of the Lyrician Complex. Although it is often referred to as a single event, it consists of 4 individual episodes of intrusions that occurred over a long time span. The final assemblage of the Columbia supercontinent generated yet another series of orogenic events, called the Laxfordian. The first occurred about 1,800 million years ago, the second 1,600 million years ago. The Lyrician gneiss metamorphosed from plutons of the TTG suite have a distinctive gray color. For long, it was believed that the Hebridean Terrain was a compact crustal block, and as more studies were performed and more events were discovered, it was expected that these would be recorded uniformly throughout. But it turns out this wasn't the case. The events that occurred that we've mentioned are not recorded everywhere, which led to the conclusion that the Hebridean Terrain does not represent a single unit, but is in fact made up of smaller terranes that gradually fused together. This map shows 10 distinct terranes from the oldest to the most recent, based on the maximum ages of the parent rocks of the Louisian gneisses. The oldest ages, of over 3,100 million years, were recorded both in the Outer Hebrides and the South mainland. The youngest age was recorded in a small terrain at the northern tip of the Isle of Lewis. The gneisses in the Ascent terrain are believed to be the most representative example of the Louisian gneisses, as they record all of the events. Studying the Louisian gneisses and their parent rocks revealed another surprising aspect. Most of the Outer Hebrides have more in common with West Greenland than with the Scottish mainland, while the Scottish mainland may be more related to Scandinavia. Now that we've discussed the Louisian gneisses and their parent rocks, let's return to the Louisian complex. Besides the overwhelming occurrence of gneisses, the Louisian complex is also made of other rocks. For example, rocks that have both continental and oceanic origin and are thought to represent accretionary complexes formed in a volcanic arc setting that were accreted to the continental margin and later metamorphosed and deformed in orogenic events. Two examples of what are believed to be accretionary prisms are the Loch Marie group and the narrow belt of sedimentary rocks of South Hebrides. The Louisian complex also contains a few igneous complexes. These are rocks that are predominantly igneous, but also contain smaller amounts of sedimentary rocks, and all of them together have been metamorphosed. These are located in the Outer Hebrides, mostly on the largest island of Lewis and Harris. The older South Harris igneous complex intruded the accretionary prism about 1,800 million years ago, while the slightly younger Harris igneous complex was in place about 1,600 million years ago. Another example of rocks are fold rocks that suffered intense deformation and, as their name suggests, are associated with faults. They outcrop on a large area in the Outer Hebrides, but are not older than 1,700 million years. There is a variety of other rocks as well, which are widespread, but the occurrences are rather small, and at this scale, they are not visible. Let's fast forward in time and stop about 1,200 million years ago. The Louisian complex had long stabilized, and the orogen had been deeply eroded. About 1,200 million years ago, the final breakup of Columbia occurred, and another supercontinent was about to form. This was Rodinia. In the previous session, we briefly mentioned that the assemblage of Rodinia generated an impressive mountain building event known as the Grenville Orogeny. The erosion of these mountains around 1,000 million years ago generated a huge amount of sediment, part of which was deposited on top of the Louisian gneisses in what is now the Scottish mainland, but back then was the marginal continent of Laurentia. The Thoridonian Supergroup comprises three groups of rocks that are similar in composition. They are sedimentary rocks, of which sandstones prevail. As in the case of the Louisian complex, what we see on this map is the outcrop area, not the entire extent of it, which is much larger and reaches as far away as the Minch and the Sea of the Hebrides. The oldest group, the Stour, is considerably older than the other groups, and its deposition in a rift valley around 1,200 million years ago is sometimes believed to be related to the final breakup of Columbia. Part of the rocks that form this group are believed to represent an ejecta blanket, that is, materials that are ejected following an asteroid impact. The material is thicker on the crater's rim and gradually thins away from it. The location of the ancient crater is debatable, but is assumed to be located on the seafloor separating mainland Scotland from the Isle of Lewis. The middle group, the Sleet, was deposited about 1,000 million years ago and occurs mostly in the south of the Isle of Skye. The youngest group, the Thoridone, was deposited about 1,000 to 800 million years ago and is by far the most representative and largest by volume. The Thoridonian sandstones were eroded in time to the point that only isolated mountains remain in place. That's the classical landscape of northwest Scotland, which is most prominent in the Assynt area, where the rocks of the Thorigonian Supergroup lie directly over the flat ground made of Lewisian gneisses. Just as in the case of the Lyrician Complex, the formation of the Thoridonian Supergroup was followed by a break in which no deposition occurred until later. Let's forward in time once again to about 550 million years ago. The last major depositional event that occurred in the mainland area of the Hebridean Terrain was that of shallow marine sediments at the margin of Laurentia. They were deposited on top of the Thoridonian and sometimes directly on top of the Lewisian gneisses. The first of these rocks to be deposited occupy a narrow strip of land from the very north of the mainland all the way to the Isle of Skye. The base of these rocks displays a prominent crust bedding, which is a very good indicator that deposition occurred in a shallow marine area with powerful tidal currents that shifted from one direction to the other. The second group that was deposited consists of carbonate rocks. They are sometimes referred to as limestones, which is not exactly correct, as limestone is not the dominant rock type, but dolostone. The difference is that dolostone is slightly harder and less easily soluble than limestone. Towards the very end of the Paleozoic era, the Neches Sandstone supergroup was deposited about 300 million years ago. The most significant outcrop in the Hebridean Terrain, although less extended than the outcrop of other rocks, is in the Outer Hebrides. The Mesozoic Era was relatively uneventful. Some sedimentary rocks were deposited and the outcrops are mostly confined to the Inner Hebrides, although the bottom of the Minch was also filled with sediments that were placed on top of Lewisian gneisses and Thoridone Sandstones. Now that we've covered the Precambrian and the history of the formation of the Lewisian gneisses, and we also briefly reviewed the Paleozoic and Mesozoic deposits, we've arrived to the Cenozoic Era, the one that brought not only one of the most recent, but also one of the most amazing events in the history of Scotland and of the world. And that is the opening of the Atlantic Ocean, more specifically the North Atlantic, about 60 to 50 million years ago. The whole west of Scotland was then the scene of major volcanic eruptions and magmatic intrusions that created the volcanic districts of the Hebrides. Although it's a very interesting topic that I was looking forward to including in this presentation this evening, we will stop here for now. I know it's a somewhat abrupt ending, and I apologize to all of you for this. It's just that I haven't managed to include all of the material in this slideshow. I will, however, make an additional one, and we will do our best to have them both uploaded on YouTube, hopefully as a single video. Thank you very much for watching and listening, and see you next week.
So that was absolutely fantastic, Alex. And fear not, we have a little short presentation which Dr. Angus Miller has prepared for us. He can't be with us this evening, but he has recorded that. So I'm going to share that with you now, and we will answer questions at the end. So after the short video from Angus, we'll go to Dr. Laura Hamlet, who is from the Northwest Highlands Geopark, to tell you a little bit about what they do there as well. So for the people who have just joined in between, just to let you know that this is being recorded. So if you don't want your face to appear on video or on YouTube, feel free to switch your camera off. And my name's Dr. Katie Strang, and I'm the Secretary of the Scottish Geology Trust. And I'm going to now share my screen, and we'll go over to Angus's presentation.
Good evening. Angus Miller here. Sorry not to be able to be with you in person tonight, but I just wanted to share with you a little bit of an insight into what all this amazing geology looks like in the ground, particularly one of my favourite parts of Scotland, around about Torridon and Loch Maree. So this is the view from the Benny Mountain Trail, looking across Loch Maree to Sleoch. And there's a famous geological view because of the contrast between the Lewisian gneiss that we've been hearing about, part of the main basement of the Hebridean Terrain, and the Thoridonian Sandstone that forms Slioch and sits on top of that old basement. And these are wonderful rocks. It's a wonderful area of mountains. And what I love about it is the contrast between the pretty ancient stuff, which lies towards the coast. And then as you go inland, you get into what we'll talk about next week, about the Northern Highlands terrain and the Moyne metamorphic rocks. But my favourite bit is the junction between the two, the Moyne thrust, and particularly it's a really interesting bit of geology just underneath the Moyne thrust, and because everything tilts to the east, underneath the plane, the line of the Moyne thrust means that as you go westwards, you get to see what deformation happened underneath the Moyne thrust and actually deformed some of the older underlying rocks. So from the same sort of view, looking to the end of Loch Marie, Inverview is just round the corner, and that's just sitting on that junction. Progress a few more miles inland and you get onto the Moyne metamorphic rocks and the Moyne thrust. But it's this interesting zone where you got a disturbance of the existing rocks as the big slab of overlying metamorphic rock moved westwards. Beautiful, beautiful mountain scenery. Benny and the big mountains of things like Leotach and Slioch, down to the coast at the foot of Glen Torridon and Loch Torridon. And it's just amazing amount of rock exposure. That's what makes this area so stunning geologically, because you can see it so well. You can stand on a mountaintop with your binoculars and you can see the different rock units laid out before you, and they are very contrasting. Picture I showed you a minute ago showed the Lewisian gneiss tends to be quite a low terrain and very, very hard rock, but it's been ground down and eroded a lot over the years. And then these like slabs of Thoridonian sandstone, originally thousands of meters of the stuff. Some places you see a lot of it, other places it's just little fragments. And on top of that, the sparkling white quartzite and pipe rock from the Cambrian period. One of the most stunning rocks in the Highlands, without a doubt. It's a very tough, forms mountaintops, but it is also susceptible to frost erosion. So you get a lot of scree slopes being created from the breakdown of this material. So this is looking roughly towards the coast, around the back of Benny, and the contrast between the layers of the Thoridonian sandstone in the lower parts, and then the quartzite sits above it in the normal sequence of things. So Thoridonian sandstone is 1,000 million years old, and then the Cambrian quartzite on top of that, it's only half its age. Pretty amazing contrast, and just in its own right. So when we go into Glen Torridon, and particularly the area that I know well is south of Glen Torridon down towards Keishorn, you get just along the edge of this junction between the two terrains of the Northern Highlands. And this is typical of what you see, the same rock units I was talking about a minute ago, but you get a sense from views like this, it's the south side of Glen Torridon, get a sense of disturbance, a sense that the even layering that was originally formed, originally part of that, these rock sequences getting disturbed. And indeed, because the rocks are so different visually, you start to pick out clues to the scale of the tectonic disturbance, because this browner coloured slab of rock running up the middle of the hillside here is the Thoridonian sandstone, and it's out of place. It should be underneath the quartzite, but you can see that with movement from the east, rock units moving westwards, this has moved up and over some of the younger rocks. So it's out of position, and it's been that's caused by compression and slabs of rock deforming, but it's deforming in a brittle sense. So this is not the deep metamorphic activity we'll talk about next week in the Northern Highlands. It's not slow folding and heating and changing. What's happening here with this junction is it's close to the surface, and so the rock slabs are sliding past each other as rock slabs, and so you get a lot of fault movement and thrusts and uplift, and so it's very common to get slabs of the older, deeper rocks that are out of position and pushed up onto the top, and this is just within this zone of deformation, beside and underneath the Moyne thrust itself. It's not the Moyne thrust, but it's driven by the much bigger slab of much bigger movement of the big slab of Moyne schist that sits on top of it all. So this is my favorite areas. I spent a month here as an undergraduate. This is where I did my mapping project, and a place of return to. But the geology is fantastic. The scenery is beautiful, and it's a very quiet place. And this is why I like this part of the Moyne thrust zone. The much more famous area is up in the Northwest Highlands UNESCO Global Geopark, and that's really appropriate for the geopark to be the northern section round about Ascent, because that is the historically important bit. That's where field parties go, lots of geologists go. But I thought tonight, rather than showing you that, I prefer, in some ways, this quieter and wilder section of the Moyne thrust zone a bit further south, because of the views like this, because you can stand on a hillside and you can trace the rock units and the fault lines across the area and see how the character of the different rock plays out in the scenery. So this is looking northwards. Peak on the right here is one of the Munros, Molshan Jarag, and the movement. So looking north, the movement of everything has been from the right to the left here, and so these slabs of rock have been pushed up and over. So we can see in the middle the brownish colour of the Thoridonian Sandstone and the sequence of Cambrian quartzite sitting on top of it, but you see that whole slab is sitting on a thrust fault that has got more Cambrian quartzite underneath it. In fact, the whole sequence is repeated several times. So here's a sort of summary of the map that I drew as an undergraduate, and just covering an area about 5 to 10 kilometers across, and going from what we'd refer to as the undisturbed foreland, the rocks that haven't been affected by the fault movement, and then as you head eastwards, eventually get to the Moyne schist itself and the actual fault plane of the Moyne thrust. But for me, the geologically interesting bit is a bit in the middle, where there's been disturbance. So each of these big black lines here shows where I've identified on the ground a fault line where rock units have moved. And so the overall sequence going from the Thoridonian Sandstone up to the white areas here, the sparkling white of the quartzite, and then a very thin set of strata which sit on top of that, but each little bit's different, and so you see it's quite easy to pick out in the ground how things have moved. If it was all the same type of rock, several kilometers thick, which had been deformed, it would be much harder to detect where all these fairly small scale movements had taken place. And the character of the rocks also controls how it moves. So the very coherent rocks like the Cambrian quartzite, it's a very tough rock, and it tends to move as a unit. Behaves in a different way from the mudstone. This one of the famous rocks from Victorian times, called the Fucoid beds. It's a brownish mudstone, and it's very slippy. So when it gets caught up in this tectonic activity, it tends to slide more easily, and you get a big wodge of it building up, to use a technical term. So that's the area. Just a small part of this complex story, but with beautiful exposures of rocks and hillsides made of different rock types. And turning sorry, just show you a little bit more of the detail of what I suggested for how this is all controlled. That naps are these individual slices of rocks that have moved, and so you get this idea of things gradually shifting and building up on top of each other, a lot of repetition, and zones where there's added complexity in some places. But the whole the whole picture gets picked out in these views and hillsides. That's a good example of a thrust fault running from top left to bottom right down the screen here. And the Thoridonian Sandstone on the right hand side belongs much deeper down, but it's been moved out of position and shoved up on top of it. And you can actually see on that junction and that line, it's very well exposed. You can see how the underlying rock's been striated by the movement of the rock mass above it. And final picture looking south to Skurigari, that sits above Loch Carron, and a completely different character of hill. This doesn't look at all like the Thoridonian Sandstone. It doesn't look like these lovely jagged quartzite peaks, and that's because it's not. It's Lewisian gneiss, and it's completely out of position. So it should be hundreds of meters, kilometers down below the surface, covered by the younger rock units. But the intensity of the deformation has brought a bit of that deep crust, and not just a small piece either. This is the start of quite a big nap that runs south towards Glenshoe. So a large chunk of the deep crustal structure has been dragged up out of position and ended up right at the top of the sequence. And I find that just really amazing and beautiful, particularly when you're standing there and you get a 360-degree view and you can sense the three-dimensionality of the Moyne thrust zone and get a sense of the power of thrust movements and these different terrains that have been crashed together on an immense scale.
So I hope everyone enjoyed that wee bit from Angus there, and thank you very much, Angus, even though he's not actually here at the moment, but I'm sure you'll watch this back. And I'm going to now pass over to Dr. Laura Hamlet from the Northwest Highland Geopark.
Thanks so much, Katie. I don't have a nice video or amazing slides or anything like that, so I was just going to kind of wing it a little bit. But really it was just to kind of talk about how this kind of asset that we've got in the northwest of Scotland can be relevant to people and the communities that live today. So I work for the Northwest Highlands Geopark, which is a charity, and the charity manages the UNESCO Global Geopark status for the Northwest Highlands. And that designation covers an area that's 2,000 square kilometres in size. But there's only about 2,000 adults registered on the electoral register in the area. So it's a very sparse population, and the communities here are, constantly fighting against the odds for survival, really. And so the vision of our charity is that the Northwest Highlands will be a thriving and sustainable rural economy, capitalising on the assets and people of the geopark in partnership with local government, relevant agencies and local businesses. And I think that the assets that we're talking about for community development are literally the geology. The underlying rocks in the Northwest Highlands is what gives the landscape its character, what's helped the communities develop into the culture that they have today, and the land use and management practices for thousands of years have all been heavily reliant on the resources that they've had available to them, as it is anywhere in the world. But in the Northwest Highlands, we've got something really special. We've got somewhere that people come to visit. We get more than 100,000 visitors a year to the geopark, and the charity basically provides activities and things to see and do for them, and visitor engagement. So we have a small visitor centre called the Rock Stop, which is a cafe and a shop with an earth science exhibition attached to it to tell people all about the area. But it also contains interactive stuff like an augmented reality sandbox and a virtual time machine that can transport you back to the beginning in the Lewisian gneiss in the formation of that. So some of the other things that we're involved in at the moment, we have a project to employ a ranger for the north end of the geopark. So our ranger Fraser, he's there to welcome visitors to the area and tell them all about the landscape. We also do small kind of infrastructure projects. So we recently put in some bike racks at Smoo Cave to encourage more sustainable travel. And we provide landscape interpretation all up the main road of the geopark, but also to encourage people to go down and explore further. We put on guided walks, we organise a climbing festival that's now taken up by the community. We can see that there's an awful lot of things that we're involved in. One of the projects that we're just coming to an end with now is a joint project with the University of Stirling to investigate past land management practices, and particularly to look at the legacy, the nutrient legacy from the geology, but also from the people that were managing the soil for agricultural purposes, right from the Neolithic period up until the present day, to work out what legacies we've got for soil nutrients in the future to help people grow food more locally and adapt to a changing climate. Also, the UNESCO Global Geopark label is something that we use in the Northwest Highlands to promote ourselves as a region. So, for example, the Scottish Government's introduced regional land use partnerships. They're in a pilot phase just now. And the Northwest Highlands Geopark was the area that was chosen for a pilot in the Highlands, and that was because of the work that we did together with other partners to develop a vision for 2045 for the Northwest. And this all came about because we have this outstanding geology in the Northwest that brought the people together to start thinking about, well, how can we use this and protect it and protect the cultural development that's happened upon it for future generations, and how can we use that to look for new investment in new industries and skills and jobs and stuff like that. So there's a huge amount you can see linked to that, and I'm quite happy to talk about the geopark all night, but I realise that there's other things that are upcoming, so happy to answer any questions that anybody might have on the Northwest Highlands, the geopark, the stuff that we do, anything generally.